This is the first lecture of 2 for the pericyclic reactions. So in this presentation, we will cover the following: a basic definition of pericyclic reactions and the types of pericyclic reactions. There are actually 3 types, but we will cover only 2 in this lecture, and the next one we will cover in the last lecture of the course. So the 2 that will be covered here in details will be the electrocyclic pericyclic reactions and the sigmatropic pericyclic reactions, usually referred to as the rearrangement, the sigmatropic rearrangement. So let's begin. Pericyclic reactions involve unsaturated systems. That's double bonds or triple bonds, but as we'll see in this case, it's mostly double bonds. So for these reactions, electrons of the pi bond and sigma bond, adjacent sigma bonds, are transformed into new bonds. So the key word here, or the key aspect here, is that pi bonds are transformed into sigma bonds. Another aspect of pericyclic reactions is that the transition states for these reactions are cyclic. Hence the word pericyclic reactions. In addition, these reactions are also described as concerted, which means that there are no intermediates. You will not find in these reactions your carbocations or the carboanions or radicals or any of the species that we have discussed earlier in the course. These reactions take place in heat or light. So these reactions are unique. So now you can see why they are a separate, they are covered in a separate chapter here. As mentioned, there are 3 types: the electrocyclic reactions, the sigmatropic reactions or rearrangement, which we will cover in this lecture, and in the next lecture we will cover the cycloaddition reactions. You'll see that's involved a very common reaction in organic chemistry known as the Diels-Alder reaction. Okay, so let us look at these reactions in terms of in terms of real molecules, or examples of real molecules. The electrocyclic reaction, an example of the electrocyclic reaction is shown here. So we have a double bond, a pi bond here, and notice in the presence of energy, that could be heat or light, and we'll see which one is needed here. Gives us this cyclobutane. So you can see here that this pi bond and this pi bond is now transformed into a new sigma bond over here, and we have another pi bond here. So that explains the transformations of pi bonds into sigma bonds. Here's the sigmatropic rearrangement. So notice here again, here are the pi bonds, here are the pi bonds, here's a sigma bond, but what it looks like is that this sigma bond here is transformed into this sigma bond here. That's unique. So that this type reaction is known as the sigmatropic rearrangement, and we'll go into more details. The last type of pericyclic reactions that will be covered in the next lecture is the cycloaddition reaction. So what this is, it involves 2 molecules. And what happens here is that a ring or cyclic product is typically formed, or is formed, because of cycloaddition. So you can see here, this portion here is right here. And of course, well, this portion here is right here, and this is our bond right here that's transformed. But we'll cover this in more details in the next lecture. So let's first look here at the electrocyclic reaction, the first reaction, type reaction, or type pericyclic reactions that will be covered. These reactions involve ring closure and ring opening, so they are reversible reactions. They take place in the presence of heat or light. So these reactions can be viewed as the formation of a new sigma bond. Let us look at an example here. So here's a conjugated polyene. And here's a double bond, here's a double bond in conjugation. In the presence of energy, this product is isolated, the cycloalkene here. In this case, it's a cyclobutene. So, but what it appears happened here is that these electrons here form a sigma bond, and these electrons here form a pi bond or double bond back here. So it's a complete transformation of bonds. So here are the pi bonds again, and here is the new sigma bond and a new pi bond. So once again, to analyze these reactions, it requires a new or a different approach than what we have seen before. So let us look at more specific examples here. So this is the EE alkene or polyene here. Notice the stereochemistry. So these reactions are stereospecific. So notice the stereochemistry of the reactant. In the presence of heat, we get the trans product. In the presence of light, we get the cis product. So you're starting with the same reactant here. So starting with the same EE reactant, in the presence of heat, we get this, trans. In the presence of light, we get this, cis. Again, that's why they are described as stereospecific, because it takes a specific reactant, stereochemistry of a specific reactant, and transforms it into a product that has a specific stereochemistry, hence specific stereospecific reactions. Here's another example. This is an isomer of this molecule. As you see here, this is the ZE isomer. In the presence of light, we get the trans. In the presence of heat, we get the cis. Again, to emphasize, these are stereospecific because it takes a specific stereochemistry in the reactant. In the presence of energy, heat or light, a specific stereochemistry is gained in the product. Okay, let us see how this happens. So let us look at a specific example here. So this is the EE24-hexadiene. As you may recall from your general organic, this is 1, 2, 3, 4, 5, 6, which means hexadiene, and it's EE because we have here the H and the H. They are on opposite sides of the double bond, so that's the E nomenclature. So this is it. But in the presence of heat, this particular specific compound gives the trans. In the presence of light, this same specific stereochemical compound gives the cis. Let us try to understand why. As we mentioned earlier, we cannot use the previous concepts of intermediates to explain these reactions. So for the mechanism, we cannot invoke the intermediate of radicals or carbocations or carboanions. We'll have to use a totally different approach. So what's done here is to examine the molecular orbitals. So let's look at the ground state of the hexadiene, and this time we're just looking at the p orbitals, because as we mentioned here, it's the pi bonds that are really of importance here. So let's look at the p orbitals for 2,4-hexadiene. Notice it has 2 double bonds, which means 2 electrons in each, which means a total of 4 electrons. So this represents here the ground state. So these are the 4 orbitals of 2,4-hexadiene: pi 1, pi 2, pi 3, and pi 4. You will recall that we need to put in the 4 electrons, so we start populating these molecular orbitals by populating the lowest energy first. Remember again that energy increases in this direction: lowest energy, highest energy on top. So this is the lowest energy. Pi 1 gets 2 electrons. Don't forget, only 2 electrons per orbital. Since we have 4 electrons, we have 2 more. So 2 electrons go into the next orbital, pi 2. We have names for these. This is now called the highest occupied molecular orbital, because it's the highest orbital that has electrons. This is called the LUMO, or the lowest unoccupied molecular orbital. So this represents the ground state of this molecule. Let's see how we can predict the product based on this model here. There's one requirement here, however, that the formation of a bond must be symmetry allowed. Let's see what that means. So we're looking at the end orbitals here of the HOMO. So this is illustrated right here. That's the HOMO, or the highest occupied molecular orbital. That's the orbital of importance, because those are where the electrons are, which means that those electrons will form the new bond. So that's the orbital of importance, pi 2. To form a new bond between this carbon and this carbon means that we'll have to rotate this entire bond right here. Let's see if we can do that, so that this comes in here, and in that case we'll have to rotate this bond over here. Why are we doing that? So that we can have here symmetry allowed overlap. So notice here the unshaded and the unshaded of these 2 carbons are now symmetry allowed, or phase allowed, so that a bond can take place right here. Notice what we had to do though. We had to rotate this one clockwise, and this bond here clockwise, clockwise and clockwise. We call this type rotation con-rotatory ring closure, because they're both clockwise. Con-rotatory ring closure. But let's see what happens to the methyl group, however. You notice that on this rotation, this goes down. And on this rotation, this comes up. So that means that we have here the trans stereochemistry for the product. So once again, this gives you a model, a way of explaining these reactions. It's different from the explanations that we've used before, when we typically invoke intermediate. So these are called concerted reactions because the electrons from the HOMO, they form the new bond as shown here. Let us look at what happens in the presence of light. So in the presence of light, we create what's called the excited state. You may recall from your spectroscopy course that in the presence of light, this energy gap here is specific. So in the ground state, as we've seen in the previous slide, we had 2 electrons here in the HOMO. But in the presence of light, there is a promotion of 1 electron into the next highest orbital, pi 3. So this now becomes the HOMO of the highest occupied molecular orbital, and this is the LUMO. So the orbital here of importance will be this one, because that's the highest occupied. Carrying out a similar analysis as we've done before to allow for phase phase symmetry to be allowed, which means that the correct phasing must be in place for the bond to form. Let's see what has to happen. This time we'll have to rotate this bond in this direction and this bond here in this direction. So we can bring this over here and this down as shown here. So here we have phase allowed, same type allowed symmetry as we had before. However, the rotation must be different. So this is a clockwise rotation and this is a counterclockwise rotation. This type rotation is called a disrotatory rotation, ring closure. Disrotatory ring closure. As you can see here, the same molecule, the same reactant. What happens here is that this rotation will bring this up and this rotation will bring this up. So you can see that now we have the methyl groups on the same side after carrying out this rotation, which is known as disrotatory ring closure, which results from the HOMO for the excited state of this hexadiene or the polyene here. So that gives an explanation for the stereochemistry that results from the specific stereochemistry in the reactant. So as a summary here, so if we have this reactant, notice the stereochemistry again. This is the E. In the presence of light, based on the symmetry requirement for ring closure, this will be a disrotatory ring closure, which will make these two groups on the same side. However, notice that if we now have the other isomer, a stereoisomer, where this is the the Z, so this is the Z, and this would be the E. Okay, let's refresh your memory here. This is the Z double bond, and this is the E double bond. Remember, Z means here the groups of highest priority on the same side, which means this and this are on the same side of the double bond, and the E means that they're on opposite sides of the double bond. So this is a EZ polyene in the presence of heat. Since we have 4 electrons here, or 4 pi electrons here, this will be a conrotatory ring closure, which will bring the two methyl groups here onto the same side. So for these type reactions, the electrocyclic, pericyclic reactions, you will have to exercise extreme care to determine the number of pi electrons that are in conjugation. After you have determined the number of pi electrons that are in conjugation, you'll have to determine the stereochemistry around the double bond. Next, you'll have to determine the reaction conditions, heat or light. Then you carry out your ring closure to make sure that it's symmetry allowed, that the orbitals overlap to form the new bond. Okay, so here's a summary of what we have covered so far. So if the number of pi electrons are 4, as we've seen before, in the presence of heat, it's a con-rotatory ring closure, which means that you'll have to exercise extreme care to determine the stereochemistry of the reactant. And if it's a con-rotatory ring closure, it will put the groups on from the double bond of the carbons of the double bond, either cis or trans. On the other hand, for the same system, for pi electrons, if it's light, it's going to be a dis-rotatory ring closure. Alright, as we've seen before, to make sure that there's symmetry allowed orbital overlap. Let's take it a step further. If we have a poly that now has 6 electrons, you may want to do that molecular orbital with the 6 orbitals, and to convince yourself that in the presence of heat, it's now a dis-rotatory ring closure to get the symmetry allowed overlap. And of course, if there's 6 electrons in the presence of light, remember now light will promote one electron from the HOMO to the LUMO to get the excited state. So we have a new HOMO based on that excitation, and that ring closure would be a con-rotatory ring closure. We won't go any further than 6, but as you can imagine, if you go 8, it goes back to the same here. So let's look at an example here, which has 6 electrons, 2, 4, 6 pi electrons in the presence of light. It's a con-rotatory ring closure. Notice the stereochemistry here. So we get this trans product. For the same molecule in the presence of heat, we get the cis product here because of the difference in rotations of the terminal carbons here for the pi orbitals. And notice here again, this is now a different stereochemistry for the reactant, and in the presence of light we get this as the product because it's now a con-rotatory ring closure. So again, this is a new type of approach to analyzing reactions and predicting the product, but it's with practice and just looking at what the requirements, you should be able to predict the products of these reactions. Let us look at the next type of reaction known as the Sigmatropic Rearrangement. This term was coined by Woodward and Hoffman, two noted chemists of this type chemistry. So for this reaction, here's a classic example here. So notice that this is your starting material and it's labeled right here with deuterium. In the presence of heat, we know that a reaction occurred because this carbon here, which has 2 deuterium atoms, now has an additional hydrogen, and it's now sp3. So this is sp2 and this is sp3. we know a reaction occurred because this product is different from this. Again, we'll have to carry out a analysis to determine how this occurred so we can predict similar reactions in terms of the product. So using arrows, we can say that this sigma bond is transformed to form a new bond here. Pi bond comes in to form this transition state here. Notice this transition state, there are no intermediates, it's just a transition state, and it forms the product. So this would be the arrow movement, or the arrows showing the electron movement to get the product. So let's look at the nomenclature of this type sigmatropic reaction. So here, we need to start numbering from the sigma bonds, or the sigma bond to be broken. So we have here this bond here that will be broken. By the way, this should be sigma bond to be broken. And as illustrated below. So we start numbering here 1 and 1, because that's the sigma bond, the CH bond that will be broken. Next, we start numbering to go to the bond that will be formed. So we go 1, 2, 3, 4, 5, and 1, 5. So these are the bonds that will be formed. So here is a representation here. So this is the bond that's being broken, and this is the bond that being formed. So we call this a 1,5 sigmatropic rearrangement. So once again, we start numbering from the bond that will be broken and go to the bond that will be formed right here. So this becomes a 1,5 sigmatropic rearrangement to give the product. Let's look at another example here. This example here is, let's look at this first. So we're looking at this reactant going to this product. We know a reaction occurred because this carbon here is sp3, and over here it's sp2, because it's bonded to a methyl group here. So we know that there's a difference, a reaction occurred. The bond that's to be broken is right here, and the bond that's formed in the product is right here. So we can see, using arrows to indicate electron movement to explain this reactant going to this product, we can see this comes out here, this comes in here, this bond's broken. This is the cyclic transition state. Notice cyclic transition state, and this is the product. Let's look at the nomenclature of the system here. Same system, bonds to be broken, or bond to be broken right here, as we can see. So that gets number 1 and 1. We start numbering to the bond to be formed right here. You can see the bonds are going to be formed right here to get the product right here. So that goes 1, 2, 3, and 1, 2, 3. So this is now called a 3,3 sigmatropic rearrangement. By the way, you know, in chemistry we tend to associate the name of the chemist who discovered these reactions with that specific reaction. This specific reaction is known as the Cope rearrangement because it was discovered by the chemist Cope. And of course here we have a Cope rearrangement involve carbon atoms. I'm emphasizing that because the next one we'll see there's an oxygen atom, and that has a different name. So let's look at this one. So here's another example of a sigmatropic rearrangement. This is now called the Claisen Rearrangement because it has an oxygen atom. So same type mechanism, same type arrow movement as we've seen before for the cope, but in this case it has an oxygen right here. So again, this is the bond that's been broken, and in the product, here's a new bond. So the new bond is formed right here. So you should be able to write the transition state, the cyclic transition state for this reaction. So let us see if we can apply this knowledge here for the last few slides of this lecture. So the question is, for the cope rearrangement shown below. I know this is cope rearrangement because even though this one has an oxygen atom, but it's not part of the rearrangement. It's just a substituent on the carbons that will be rearranged. So the question is to predict the products. Predict the product for this reaction and predict the product for this reaction. Notice again that these reactions take place in heat, not light, because we're not exciting the molecule. We're just closing the carbons here so that we have symmetry allowed closure. So as you can see, let's carry out the analysis before we actually see the answer. So as you can see, this is the cope rearrangement. So here's our double bond, here's a double bond. So as you can imagine, a new bond will be formed here, and these electrons will pop in and out to form this rearranged product. Let's look at this one. As you can imagine, here are the pi bonds, here are the pi bonds. So as you can imagine, for the Sigmatropic rearrangement reaction, these electrons can come out, these electrons out. Here's the sigma bond that will be broken, and here's the sigma bond that will be formed. So you should have an idea of what the product should look like based on this rearrangement, or the Sigmatropic rearrangement. So let's look at this. So this is a 3-3, as you will recall, 1, 2, 3, and 1, 2, 3. Well, actually 1, 2, 3, and 1, 2, and 3, because this is the bond that's been broken. And as you can see here, here's the mechanism, here's the product, here's the mechanism. This comes in, that comes in. Here's a new bond that's formed right here, and here it is. Here's this bond that's broken, and it's not here. So this is the cyclic transition state, 6-membered ring cyclic transition state. I should point out at this point that this 6-membered ring transition state has 6 electrons. 2, 4, and 6 electrons, and you will recall from Huckel's rule that if a cyclic system has 6 electrons, it's stable, it's aromatic. So this intermediate here is not intermediate, pardon me, this transition state, let me make that correction again, this transition state, not intermediate, is aromatic because of the 6 electrons based on Huckel's rule. Let's look at the next reaction. So as you can see, it's just again a 3-3 sigmatropic, because here's the bond that's been broken, here's the bond that's been formed. So 1, 2, and 3, 1, 2, and 3. So using the electrons, or the electron movement formulism, bond is formed here. These electrons come in, this bond is broken, and you can see this bond is gone, and this bond is formed based on this electron movement. This is your transition state, cyclic transition state, with 6 electrons, 2, 4, and 6. Pretty stable transition state, which goes on to form this as the product. I should point out, however, combining chemistries here, this molecule is known as an enol. So this is the en and the ol. We know from previous chemistry that the enol is not stable. It quickly tautomerizes to give the ketone. as shown here. So this enol tautomerizes to give the ketone, which is now more stable than the enol, because we have a carbon-oxygen double bond, which is a much stronger bond than the carbon-oxygen single bond. So this is called the keto-enol tautomerization. Let's see a possible mechanism for that tautomerization. Here again is the enol, here's the keto form, so you can imagine these electrons coming in to form this intermediate here. Notice this is an intermediate now because this is not a pericyclic reaction. This is a keto-enol tautomerization. Proton transfer from here to here gives the ketone as the product. So once again, I think this is the last slide, and yes it is. So once again, for these two pericyclic reactions, the electrocyclic reactions and the sigmatropic reactions, read up in your text, practice it. You should be able to recognize these type reactions. You should be able to predict the product of these type reactions. You should be able to recognize that these reactions are stereospecific, so that if there's a specific stereochemistry in the reaction, in the reactant, these will give you a specific stereochemistry in the product. So this is quite a bit, but with practice over the next couple of weeks before the final exam, you should be able to, or you will master this material. So continue studying hard, and I will post the final lecture, which will be on Cycloaddition pericyclic reaction shortly before the week is out. Okay?